Okay, today we're going to talk about inference for the difference of two means. This is different than what we did last time when we did the mean of differences, which is matched pairs. This is where we're going to have two separate samples from two distinct populations, so it'll be a difference of the means. Up above, we have two sample problems. So the goal to compare the responses to two treatments or to compare the characteristics of two populations. That's our goal. That's what we're doing. We're comparing two separate groups. We have a separate sample from each of the treatments or each of the populations. Again, two separate groups, and we're comparing them. And we're going to be using T procedures. So when you don't know the mean and especially the standard deviation of the population, we use the T procedure. Two populations. So we have, for our conditions, two independent simple random samples from the two distinct populations, and you must check and discuss the independence between those two samples. Mostly the independence is making sure that they are different, that you can't be a member of both groups. If you have the characteristic of one group, there's no way you could also have the characteristic of the other group. And then both populations are normally distributed. Again, it doesn't have to be the population, it's the sampling distribution. Needed to fix that. So both sampling distributions are normally distributed by checking both populations are normal. So that's one way to do it. So if the problem states that both populations are normal, then your sampling distribution would also be normal. Or if you don't have that information, then you go to the central limit theorem and make sure both have a large enough sample size. You will probably be using the central limit theorem a lot more often than having the information that the populations are normal. And then again, if you don't have that, you could plot the data if you had the data. Okay, if you don't have the data and you don't have the other two, then you can't check for normality, and that condition would then not hold true. So then you could not do the procedure. And then of course we have our 10% condition that you would check on each of the samples separately. You would check the 10% condition. Okay, so those are the conditions. They're the same as before. Only thing is that now they're all doubled. So you have to check it for both populations. So you have to check the simple random samples twice and make sure the two samples that you have are independent of each other. You have to check the sampling distribution for both groups. So you have to do that twice. And the 10% condition you have to do twice. Otherwise, it's exactly the same as what we did before. All right. Standard deviation, or the standard error. Remember, the difference between them is just whether or not we know the population standard deviation, or if we have to use the sample because we don't know the population standard deviation. If you did know the population standard deviation, we could use T procedures, but as I mentioned before, that's not going to happen very often. So more than likely, we are going to be using our standard error and using this one a lot more. So since we are doing the difference of two means, we will be doing the standard error for one of the means. And remember, this part here, that's the variance. And so it's the S1 squared over N1. And then the standard error for the second group, which is also the variance under the square root. So you add the two variants together, and then you take the square root of that, gives you the standard error of the difference of the two means. So now we'll take a look at the two sample T procedures. We'll look at confidence intervals, and we will look at the hypothesis testing. So if we have two sample T procedures, and we're taking two simple random samples, one of size N1 from a normal population with unknown mean, and another independent simple random sample of size N2 from another normal population of unknown mean, then your confidence interval would be this. Okay, so we have x bar 1 minus x bar 2. That gives us our statistic, plus or minus our T star. Okay, that's a T, so there are going to be some degrees of freedom associated with that. Okay, so note you're using the T star. And then our standard error, which we just mentioned up above. So then down here, it talks a little bit about the TK distribution. So the K represents our degrees of freedom. And to find the degrees of freedom, we take the smaller of the two. So N1 minus 1, N2 minus 1, you use whichever one's smaller. It gives you a wider interval. It's a little safer. Then we can do that calculation. There is a way to get an exact degrees of freedom. You would end up having a degrees of freedom with decimals. It's a calculation you will not have to do on your own. But if you use the calculator to do any of these calculations, the calculator is going to use the exact degrees of freedom. So you have to make sure that your work and the degrees of freedom match. So if you're going to use the calculator, you have to report what the exact degrees of freedom are. If you don't use the calculator, you're going to set it up by hand, and you're going to use the smaller of these two, N1 minus 1 and N2 minus 1, and use the table to find your T star, then make sure you identify which of these you're going to use. And when we do that, typically, I would write degrees of freedom equals the smaller, so I use min of N1 minus 1, N2 minus 1. That way you are reporting how you're going to calculate the degrees of freedom, and then you identify which one is which. Okay? So that's how you would write it to show your work for the degrees of freedom, and then plug in the numbers and calculate or identify which one is the smaller of the two, so we know which one you're using. Now don't forget, if it's a degrees of freedom value that's not in the table, you have to round down, okay, to the next smallest number that is in the table. So keep that in mind as well. Now we'll move on to the hypothesis tests. Remember, the procedures for these are the same. So you go through all the same parts of the confidence interval, all the same parts of the hypothesis test. We're just looking at the different calculations and how we would then calculate the degrees of freedom for the two samples. So the hypothesis test, we are testing the hypothesis that mu naught equals mu 1 and or h naught is mu 1 equal to mu 2. Okay, so that the two means are equal. That's what we're testing. So we're making that assumption that they are equal, and there's going to be some kind of an alternative that's less than, greater than, or not equal to, and we are doing the test to see if there is evidence that the alternative may be true. So to calculate the two-sample t statistic for the hypothesis test, you subtract x bar 1 minus x bar 2. That's your statistic. Now technically there is a parameter that would be mu 1 minus mu 2, but because of our null hypothesis being that those two things are equal, that's going to be 0. And then your standard error at the bottom. Okay? So again, I have a tendency not to put the mu 1 minus mu 2 because it tends to be 0 most of the time, but it doesn't hurt to make a note of that. And use p-values or critical values for the TK distribution. So after that, then you look everything up. To do the degrees of freedom, K, we do it the same way as we do it for the confidence interval. It's going to be the minimum of N1 minus 1 and N2 minus 1. Okay, whichever of those two is smaller. Again, if you use the calculator to get your calculations, it's going to give you the exact degrees of freedom. So you need to write down what the calculator tells you the exact degrees of freedom are. Make sure your answer matches with the values that you are giving. If you're going to use this, you need to make sure that that's what you write on your paper and that the numbers you put on your paper for that formula match. So you're using your T table with the appropriate degrees of freedom to calculate what the p-value will be. Everything has to match. You can't mix them up. So we've got our hypothesis test, our confidence interval from before. So I want to go through again real quick what that process is. So for the confidence intervals, you state your population or populations. If you're doing a two-sample, you have two separate populations. You have to describe them both separately. So I should have a population 1 is, and tell me what it is. Population 2 is, and then you tell me what it is. Yes, there is a lot of writing. Okay, I've told you that before. So don't forget, you have to describe them both separately. Same thing with the parameters. Okay, you have parameter 1, and you describe what it is, and parameter 2, and you describe what it is. So you just state your populations, your parameters, check your conditions. Okay, and if it's a 2-sample, the conditions are doubled. You have to check them twice, once for each sample. After the conditions, you can do the calculation. And then for the confidence interval, once you've calculated what your interval is, then you state your conclusion, which is the interpretation of the confidence interval that you calculated. Then we have our hypothesis test. Okay, so the process, you state your parameters. Again, because we're dealing with 2 samples right now, there are going to be 2 of them, a mu1 and a mu2. So mu1 and a mu2, so you have to describe each one of them separately. So you'll have 2 definitions. State your hypotheses. So the null hypothesis, mu1 equals mu2, and the alternative, that it's either greater than, less than, or not equal to. Okay. So you state your hypotheses, check your conditions, then your test statistic, and any other calculations that might go with that, such as calculating degrees of freedom. You need to state that and show it if you're using your t-statistic. Then your p-value, and your conclusion. Okay, hopefully I didn't miss any steps. So these are the processes that you use for each of these types of inference procedures. So you have your confidence interval and your hypothesis test. Okay, next we're going to look at some of those things that I said we'd look at real quick at the end. One are the exact degrees of freedom. This is the calculation that is used to calculate the exact degrees of freedom that the calculators use for 2-sample tests. You do not need to know this. I like to show it so that you guys know where that value is coming from. The calculator does use this to calculate the exact degrees of freedom for 2-sample tests. If you use the calculator to get your p-value, especially in your z value, or t-value, I'm sorry, the t-value and the p-value, then you need to make sure that you write down the degrees of freedom that the calculator has calculated, because this is what it's using, and it's different if you use this number opposed to the min value that I showed you earlier. Okay, so this is going to give you, using the degrees of freedom and finding the minimum, that is going to give you a smaller number for degrees of freedom, and usually a bigger t-statistic or t-star critical value, whereas the other degrees of freedom doesn't, because it's more exact. So it tends to be a little bit smaller. So just be careful with which one you're using and make sure it's consistent with your t-value and p-value in your tests and confidence intervals. The other thing I wanted to point out just real quick was the pooled 2-sample t-test. We don't use the pooled in the AP. It is on your formula sheets. I think when it first started, they initially thought they might use it some. You do need to know when you would use it. Population variances or the population standard deviations, when they are expected to be the same, then you would use a pooled 2-sample test. And then this is how you calculate the SP, which is the pooled standard deviation, and that is what's used in this formula from the formula sheet, if you remember that special case. And this pooled value is what is put into that standard deviation spot. But you can only do that if you could do a pooled test, which you can only do if the standard deviations from the population are the same, which we usually don't know. So we don't use this test for the AP. However, the LBCC does use this test, so we'll go into it in a lot more detail when we start reviewing after the AP exam for the LBCC exam.